Okay, so welcome to one more edition of the Physical Seminar of Philosophy of Physics and Cosmology. Let me start by thanking Dr. Philip Pamplona and Professor Vinicius Carvalho from Physicus for organizing the event. Today we are going to have a session in a new and very exciting framework, which I think points the way towards a wave memory interpretation of quantum mechanics, more precisely reinstating the pilot wave ideas of Louis de Broglie and featuring the recent emergent area of hydrodynamic quantum analogs. And together with us, I have the very great pleasure of having Professor John Bush from MIT giving a talk precisely on hydrodynamic quantum analogs, and also Dr. Adam Kay, a former postdoc in the mathematics department at MIT, and also the author of an excellent book about the foundational ideas of quantum mechanics called Escape from Shadow Physics, which I highly recommend. I will start by introducing John Bush, which I thank very much for being here. It's really a wonder. John Bush is a professor of applied mathematics at MIT, directs the Applied Mathematics Laboratory, the center of the experimental branch of his research. He initially began interested in geophysical and environmental flows, but then shifted towards surface tension-driven phenomena and their applications in biology and epidemiology. Well, what a word to say for Portuguese. For the past 14 years, his research has been focused on hydrodynamic quantum analogs. And so, John, thank you. You have the floor. You can
Very good. Thanks for the kind introduction. It's a pleasure to join you all remotely, though it is. Now I can't. There we go. Okay. So, I wanted to begin this venture was started in 2005 by Yves Couder and Emmanuel Faure. And I've been working on it for 15 years. I started in 2010, and so I've collaborated. I've had many graduate students who have gone on and are now professors, likewise with postdocs, one of which, Adam, you'll be hearing from later. And this has all been supported by the National Science Foundation. I've also received some funds from the Limitless Space Institute and most recently the ONR. Okay, so let's get started. So the general view of the universe you come away with after an undergraduate physics degree is that the classical world, you have this notion of classical determinism. Given the initial conditions, you can predict the unique outcome of an experiment. So the macroscopic world is deterministic. Of course, then a little bit later, you realize that there are practical limitations to predictability, and these are predictability is basically constrained by chaos. So if you have a sufficiently complex system, things become practically unpredictable, as is the case with the weather, although we know what the governing equations are. Now, hereditary mechanics is sort of a subset of classical dynamics that people don't study terribly much. And these are systems with memory. So their evolution is influenced by their past. So in order to predict the evolution of a system, you have to know both the initial conditions and its history. And so the goal of this talk and the HQA venture is to show that pilot wave hydrodynamics demonstrates how classical hereditary mechanics can give rise to behavior which is taken as evidence of non-locality in quantum mechanics. So the question arises, do we need quantum non-locality? Okay, so quantum mechanics, so this is a wave theory that predicts the statistics of microscopic particles. It doesn't describe their trajectories, and worse yet, the standard interpretation suggests that that there are no such trajectories. There is no underlying dynamics beneath quantum statistics. So their entire description of, for example, the free particle is the association of this particle with a wave. So it has a frequency prescribed by equals h bar omega and a wave number prescribed by p equals h bar k. So again, you're associating a particle with a wave, but where is the particle and why does it move? And it's all well and good to say, well, we only have the statistics, we don't know what the dynamics are, but denying the dynamics is taking things in a rather extreme direction. And so the insistence on the completeness of quantum mechanics as formulated has led to long-standing difficulties that you're all very well aware of, the proliferation of quantum interpretations and an abundance of paradoxes and odd language. So I won't get too far into that. You'll hear more from Adam on the subject. But so hidden variable theories in quantum mechanics. So these are those theories that would try to complete quantum mechanics through developing a theory of particle dynamics, so particle trajectories. And these generally involve the interaction of a particle with a guiding wave. So in 1926, before the very notion of quantum interpretation developed, de Broglie proposed a double wave pilot wave theory. So he imagined a particle has an oscillation, an intrinsic oscillation, which excites a wave, and then it surfs on that wave, and then this dynamic somehow gives rise to the emergent statistics, which are consistent with quantum theory. So this is, he predicted electron diffraction and won the Nobel Prize on the basis of this physical picture, but that physical picture was ultimately rejected in favor of no physical picture. Okay, so in 1952, Bohm presented a single wave pilot wave theory. You basically had the particle being guided by the wave function, as we'll come back to that later. It's basically a dynamical reformulation of a statistical theory. Nelson proposed stochastic dynamics, that you can think of quantum dynamics as kind of a random walk. And again, we'll touch on that a little later. And De La Peña and Cheto and others have developed stochastic electrodynamics, and their physical picture is precisely the same as de Broglie's. The particle has an intrinsic vibration, and it interacts with the background field, in their case, the electromagnetic quantum vacuum. And we'll see that that physical picture of de Broglie and De La Peña and Cheto is actually engendered in this classical system, hydrodynamic system that I'll be discussing today. Okay, so in 2005, Yves Coudert and Emmanuel Faure in Paris discovered this hydrodynamic pilot wave system in which a particle moves in resonance with a guiding wave. So it is indeed the first macroscopic realization of the double solution pilot wave dynamics proposed by de Broglie in the 1920s. And lo and behold, it exhibits several features of quantum mechanics, of quantum systems that were thought to be exclusive to the microscopic realm. So the questions we're addressing: what are the key dynamical features responsible for this quantum-like behavior? And we've really answered that question. What are the potential and limitations of this hydrodynamic system as a quantum analog? This is ongoing work in the lab. And can it guide us towards a rational theory for quantum dynamics? And I'll describe some of our attempts to address the latter problem in what follows. Okay. So the system is very simple. This is a dish about yay big, and it's being driven around 50 hertz. And above a critical vibration amplitude, you get a standing field of Faraday waves. So the control parameter is the vibrational acceleration, which is the amplitude times the frequency squared. And when that exceeds an acceleration which is around 4 times gravity, you excite the standing field of Faraday waves. Okay. And all of these experiments are done below the Faraday threshold, but when you put a drop in it, it locally excites waves. So it turns out you can levitate a droplet on the millimeter scale, because the thing's again bouncing around 50 hertz, so 50 times per second, and the air layer between the drop and the bath does not have time to drain during that impact. So it's basically sustained indefinitely on the surface, and in a certain parameter regime, this was discovered accidentally by Yves Coudert. These drops start self-propelling, and you can see that this object has both particle and wave components. You basically have a particle dressed in a quasi-monochromatic wave field. The wavelength is that of the Faraday waves you would get if you cross the threshold, but again, you're below the threshold. If the drop weren't there, there would be no waves. You just have the interface moving up and down. The wave and the particle are intimately coupled. Without the wave, there would be no particle motion. And of course, without the particle, there would be no wave. And the system is non-Markovian or hereditary, in the sense that, of course, the entire system is Markovian. It's a classical system. The only the complication comes in when you describe the particle dynamics. So the particle dynamics, the particle responds to the local slope of the wave. And but that slope depends on its history, because every time it bounces, it lays down a wave. And so the local slope of the wave is prescribed by all of the waves that's laid down along its path. And so you have to integrate backwards in time to get this local slope. And it's in that sense that it's memory dependent. And all of the quantum features arise in the high memory limit, where these waves are very persistent. And so you have to integrate very far back in time. So that's sort of a key feature, is memory. You think of the bath as the memory of the system. Okay, so the first quantum analog was done by Yves and Emmanuel in Paris. So they basically send these walkers towards slits, and they get a diffraction pattern. So the big puzzle in quantum mechanics, and again, you get the insistence from Feynman that this is absolutely impossible to understand, and then you see it and you say, oh, well, that physical picture, that's what Breuil said, and it works perfectly well. So the mystery is, how is it that these coherent statistics emerge when the particle passes through one at a time, right? So it's called single particle interference, and that's the real mystery, the fact that you get a coherent statistics despite the fact that experiments are done one at a time. And so this system captures that, and there have been many revisitations of these experiments, and it's been done. We've done it also theoretically, and it is a robust feature. The actual details of the diffraction pattern are different, but so what? You don't expect the private wave of the walking droplets to be precisely the same as that for quantum systems. Okay, and another early analog, which we're going to discuss in some detail, is that of a walker in a rotating frame. So the walker moves at uniform speed in the rotating frame, and when you have this, your undergraduate mechanics tells you that you're going to have a balance of the outwards inertial force and the inwards Coriolis force. So you get inertial orbits, and the radius of which decreases with the rotation rate. So this is the Walker speed v, which is constant. So as you increase the rotation rate, you tighten up the circle of the inertial orbit. So that's what you would get classically, and that's what you get at low memory when the wave field is relatively short-lived. As you approach the Faraday threshold, so you increase the memory, you get closer to the Faraday threshold, the particle starts interacting with its own wake. As you can see here, top right, the particle is moving on a corrugated surface, and it's basically a circularly symmetric wave field centered on the center of the orbit, and it's only stable on certain radii because it is interacting with its own wake. So you see the emergence of quantized orbits. Okay, and the quantization length in this and all other hydrodynamic quantum analogs is the Faraday wavelength, which is again the wavelength you would get if you crossed the threshold. Okay, and so there we see orbital quantization arising, and they pointed out this analogy. So the Coriolis force acting on a mass m moving in a uniformly rotating frame is takes the same form as the Lorentz force acting on a charge q moving in a uniform magnetic field. So these quantized inertial orbits are analogous to Larmor levels in quantum mechanics, and here again the Faraday wavelength plays the role of the de Broglie wavelength. And we'll use that analogy a little later in the talk. So we basically developed, so I do fluid dynamics. I did a lot of work on how insects walk on water. And so when I saw this system, I said, oh, I can definitely sort out the fluid mechanics of this system. So I won't get into the details, but I'll just show the sort of end result, which is, and we use this nice trick, which is, if you strobe the dynamics, the particle's in fact bouncing along, but if you strobe the dynamics, that is to say you grab one frame per bounce, then you just see it gliding along the free surface, as we see here, dressed in this quasi-monochromatic pilot wave field. And so we can describe that dynamics as follows. And so here we see how memory enters in mathematically. So we have mass times acceleration of the drop, we have a drag term, and then we have the wave force term, which is of course the interesting one. And to get that, you have to integrate backwards in time. So basically, as it moves along the path, it generates a Bessel function. And so in the stroboscopic approximation, you imagine that it's moving and emitting waves continuously. And so this is the form of the wave force. So you have an integration over Bessel functions, and you have this temporal damping at a rate prescribed by the memory of the system. And so the memory is basically prescribed by how close you are to the Faraday threshold. So this is, again, the vibrational acceleration. This TD is just the time scale of decay of the waves in the absence of vibration. This is the Faraday period. But so the control parameter is the vibrational acceleration. As you approach the Faraday threshold, the memory becomes very long. And so you have to integrate backwards in time over many bounces. Okay, so then you have this integral differential equation. So for math fans among you, you'll realize that once you've got an equation of this form, you can do play all sorts of mathematical games. In particular, you can assess the stability of various dynamical states. So we predicted the transition from bouncing to walking and the stability of various states, including these lattices, droplet lattices, and so here, for example, we start with a ring of drops top left, and as you increase the memory, they go unstable, so you can do linear stability theory. And top right, if you confine a bunch of drops to a circular annulus, you'll get a solitary wave propagating around. And again, we've basically done the math on that, but these are sort of asides in terms of quantum analogs. But okay, so let's return to the second analog, the pilot wave dynamics in a rotating frame. So now we take our trajectory equation, we add a Coriolis force, and we seek orbital solutions. So motions with uniform radius and angular velocity. We get a nonlinear system of equations in R naught and omega, which we can solve, and so we get solution curves, and we can assess their stability. So the stability is prescribed by the color of the solution curve. Blue, the solutions are stable, then the curve is indicated in blue, and red means unstable. So you see the origins of the quantization or the destabilization of the orbits with certain radii. Okay? And that's at sort of intermediate low memory. At high memory, the states become progressively more unstable, and you get so the green line indicates that the orbits are unstable and should wobble as they fly off, and this is indeed what happens. And it turns out that nonlinear effects can come in and actually stabilize things which linear stability theory would say are unstable. So why is this interesting? So what's interesting is how is it that you can get a sort of superposition of states? Okay, so this is the first paradigm for quantum-like behavior from this hydrodynamic system. So as we increase the memory, so if we have a stable circular orbit, if we increase the memory just incrementally, it goes unstable and it goes into this mess of a trajectory, but that mess of a trajectory actually has structure in it. It's actually jumping between unstable circular orbits. So if we plot the radius of curvature as a function of time, you see that there are plateaus, there are preferred values for the radius. And so again, you have this physical picture of the particle switching intermittently between unstable quantized orbits. And so then this sort of, in quantum mechanics, I would say this is a superposition of states. And here we would say it's a superposition of dynamical states, which arises from the chaotic dynamics. Okay, and the other thing that we saw from this study is the possibility, so at very high memory, the solution curve actually touches down on the rotation, the vertical axis, which is zero rotation rate. And so this suggests the possibility of a drop just moving in a circle trapped by its own wave field. And so we call these hydrodynamic spin states. Turns out these are unstable in the parameter regime that we looked at. There's been some recent experiments in Paris where they've actually found these states. And we'll see that they come up in our 3D pilot wave modeling, which Adam has been leading. Okay, so here's another nice analog. So what I love about this system is it's so rich. We said, well, let's look at scattering. No one's looked at scattering. So we had a walker approaching a submerged pillar, and you'd think it would just kind of hit it and bounce off. But in fact, you get something rather interesting. It is deflected along a spiral, and it's not just any spiral, it's a log spiral. So let's play a game here. Let's do as they do in quantum physics and pretend that there's no pilot wave. So then we can ask the question, what would the effective force need to be if applied at the position of the pillar to give rise to this trajectory. We know in reality the reason it's being deflected from a straight line, walkers always want to move in straight lines, unless their wave field is distorted by other droplets or some topography, some disturbance. So it would move in a straight line, but its pilot wave is being disrupted by the presence of this pillar. But it's doing so in such a way as to give rise to this logarithmic spiral, which is quite remarkable. And if you look at so you can basically find out what the applied force that the pillar would need to be to give rise to this trajectory, and it's a lift force, that is to say it's perpendicular to the direction of motion, so it's proportional to the cross product of the instantaneous velocity of the particle and its instantaneous angular velocity around the pillar. And so this looks like, again, given the analogy between the Coriolis force and the Lorentz force, it looks as if it's behaving like a charge moving in response to the magnetic field associated with its own current. So this looks like hydrodynamic self-induction. Okay? So be that as it may, I think that's fascinating, and we still don't understand it entirely. But this is an example of basically wave-mediated forces giving rise to apparent action at a distance. So that would be, again, if we denied the presence of the pilot wave, we would infer a non-local force being applied at the position of the pillar. Okay? But we know that in reality, the forces are wave-mediated. Okay, so here's another one. This gets us to our second paradigm for quantum-like behavior. So Friedel oscillations, when you have electrons zipping along on the surface of metal and you have an impurity, they scatter off it, and this is basically the PDF of the electrons, so the probability of finding them at a given position. And so you see concentric waves with the de Broglie wavelength. And so here we have a droplet approaching, instead of a pillar, we now have a deep region, a well. So it's actually drawn inwards. The things they always want to move into deeper fluid to minimize dissipation. And as it exits the well, inline oscillations are excited. And so as a result, so here we have, these are droplet trajectories, and they're color-coded according to speed. And you'll see, if you look at the trajectory coming out, as it's exiting radially, they're actually inline oscillations in speed. And so these then, ultimately, there's a correlation between position and speed. As a result, there's a statistical signature, which looks like concentric circles centered on the well. And so it looks very much like Friedel oscillations. Okay. And again, so the sort of weakest conclusion we can make is that Friedel-like oscillations are not inconsistent with the notion of particle trajectories. Of course, in their theory, there is no notion of trajectories. They solve Schrodinger's equation with a scattering potential, and they're done. Okay, and this leads us to, this is actually, I'm not going in chronological order. This is my favorite HQA. So this was done, the first thing that we did in the lab. Dan Harris is responsible for the precision of the experiments. So, and the other reason that I like this so much is this is sort of, when I was thinking about getting involved in this venture, I thought, well, what do I remember from my undergraduate quantum mechanics? And I said, oh, particle in a box. Let's try particle in a box. And this is basically particle in a box, but the box is circular. And also when I was an undergraduate, they hadn't done these experiments. So you'd solve the problem. They say, oh, it works. The theory can't be questioned. But now they've actually done the experiments. And so there is something to compare to. And so these are experiments done by Cromie principally and Eigler. And so this is a quantum corral. Note the scale is 75 angstrom. So these are negative atoms which act to bound the electrons as they zip around it within the circle. And you see the emergence of statistical signature with the de Broglie wavelength. Okay. And so I said, well, what happens if we do this with bouncing droplets? And so here we go from 75 angstroms to 3 centimeters, and we have this very complex chaotic trajectory. It's again color-coded according to speed, and it's such a messy thing. Nothing coherent surely will come of this, but you let it run, and in the fullness of time, which is about an hour, you see a correlation between position and speed. And so you get an emergent statistical behavior, which is reminiscent of that arising in the quantum system. So again, these emergent statistics in this system are not inconsistent with the notion of particle trajectories, and we can get these coherent wave-like statistics from chaotic pilot wave dynamics. Okay, so the physical picture is that of 3 timescales. So you have the timescale of particle vibration, which is the bouncing in our system. Then you have this sort of strobe dynamics where the particle glides along, and that's around, so it's again, they're bouncing around 50 hertz, they're moving at a few millimeters per second. And then you have the time scale of statistical convergence, and that's about an hour. So the real miracle of this system, you know, given that we went from 75 angstroms to 3 centimeters in length scale, it could have been that this time scale of statistical convergence was a decade or a millennium, but it was 1 hour, which is about as long as you can expect any grad student to be engaged with an experiment. And so we can resolve all 3 of these timescales, and that's the real beauty of the system. Okay, and again, so the inference is quantum mechanics has a theory which describes the statistics, but they're missing an underlying dynamics of this same form. Okay, and so one thing we noticed, we did some more corral experiments with elliptical corral, and we found that, so at any given instant, the wave field is quite complicated. It doesn't look like, say, the wave mode of the cavity. It's very complex, centered on the particle. But if you average it, the average wave field looks like the statistics. Okay, and so you can actually, we've proven what this Matt Dury, who's contributed a great deal to this venture, derived the following results. So the average wave field is can be expressed as the convolution of the statistical of the PDF mu and the wave field of a bouncer. So that depends on the memory. That's the wave field that you would get if the droplet is just bouncing in place. So you can see how this evolves as a function of memory. Okay, so if you convolve the bouncer wave field and the statistics, you get the mean wave field. Okay, and so why is this an interesting feature? Because on average, that's what the particle is seeing. So that's a self-potential generated by the droplet. Okay, and so this connects us to Bohmian mechanics, as we'll see in a moment. But so basically we have 3 paradigms for macroscopic quantum behavior, and all of them rely on the drop navigating its self-potential. Okay, so again, the self-potential is its pilot wave. So in the orbital pilot wave dynamics, we saw that quantized orbits emerge from the dynamic constraint imposed on the droplet by its quasi-monochromatic wave field. And then in the chaotic regime, you get the sort of superposition of states, which results just from intermittent switching between unstable periodic orbits. And so we also saw these inline oscillations. So in the Friedel oscillations, as the particle crossed the well, you get inline oscillations, and this gives rise to a correlation between position and speed, and so a statistical signature with the Faraday wavelength. And then in the corral, it's the most complex, and we're still really unraveling this now in the group. And you basically get chaotic diffusive motion over the mean pilot wave field. And here, in fact, in describing this third paradigm, you have to relax the stroboscopic approximation. Variability in the vertical dynamics is actually important, and the system is subjected to ponderomotive effects. And so basically you have the high, which arise in E&M when you have a charge interaction with a high frequency electromagnetic field. So in any case, but you get this sort of diffusive behavior, and it's sort of evocative of Nelson's stochastic mechanics. Okay, and so now we have a grocery list. I don't have time to discuss all of them, so I've just discussed some of my favorites. But the list is growing, and it will continue to grow. And so really, the system shows, again, how classical hereditary mechanics can give rise to behavior taken as evidence of non-locality in quantum mechanics. So we do not see, we of course know that our system is entirely classical, entirely local. Nevertheless, we can come up with rational explanations for many of these quantum systems where they have to invoke magic of one form or the other. Okay, and so it of course begs the question, can a more general pilot wave theory capture more quantum-like features? So we've been developing this generalized pilot wave framework. So we retain the key features of the Walker system, in particular memory, resonance, and this quasi-monochromatic wave field, but we go beyond the range of the hydrodynamic system. So we can also consider different waveforms and so forth. So we can then discover new quantum-like features. For example, we'll see spin states, and we can go from 2D to 3D, which is work Adam's been doing. And then it also provides a platform for connecting to existent quantum pilot wave theories. Okay, so let's get going. So basically, this is our trajectory equation. We just non-dimensionalized it slightly differently. So there are, of course, three terms. There's inertia, drag, and wave force. And so they're necessarily two-dimensionless groups governing the system. So one is the proximity to threshold. So that's basically our memory parameter. It tells us how long-lived the waves are. And the other is this kappa naught. So this is basically the ratio of inertia to the wave force. And it turns out, so one can span this entire regime in range in gamma from 0 to 1 in the lab. But in the lab, kappa naught is strongly constrained. So these drops only drops of a certain size can walk in the lab. And so kappa naught is actually constrained to lie between 0.8 and 1.6. What happens if it's 10 to the minus 6? What happens if it's 10 to the 8? Can you capture more quantum-like features? So can we get spin states, for example? When is orbital quantization the sharpest? And so these are questions that we're asking now, and addressing them with this generalized pilot wave framework. And in short, you get quantum-like features in the large memory, so high memory, small particle inertial limit, which kind of makes sense. In that limit, the wave is dominating the dynamics. Okay, so this is the sort of summary of what happens for the free particle in 2D. So kappa naught is again particle inertia. So you can get spin states in the low particle inertia case. So gamma here, so this is zero memory. This is infinite memory up here. So all the action happens here in the small particle high memory limit. And so if we zoom in there, you see these spin states and various close cousins. Generally, you just have straight line motion, and this whether they're overdamped or underdamped indicates their response to inline perturbations. But then you get to higher memory and they go unstable, so they then start tumbling, and you get a sort of a random walk with the diffusivity, which is proportional to the wavelength, the Faraday wavelength, and this is sort of, again, you have the same sort of physical picture in Nelson's mechanics. But in any case, you get much richer dynamics in this generalized pilot wave framework, in particular spin states. Okay, and so with Adam and Matt Dury, we've been looking at 3D pilot wave dynamics. So now we have a spherical Bessel function wave kernel, but otherwise things are very similar. So in particular, as the memory increases, you go from a bouncer to a walker, and the wave field now takes the form of a sort of concentric bullet shape form. And again, so self-propel above a critical memory. And so again, it's spherically symmetric, but when perturbed, the thing will start going, right? And so Adam discovered you also get the chaotic regime, so the thing moves in a straight line, then it'll move in a very wonky, erratic fashion, but then it will lock on to these helical states. Okay, so the thing is moving along, it's basically constrained to move along a helix by its self-induced pilot wave field. And this, if you think of this, if you sort of zoom out, and just imagine, this is a particle moving in a straight line. It's a particle with an intrinsic angular momentum, right? So it suggests that you can have, from a classical pilot wave dynamics, you can have a particle with intrinsic angular momentum. Okay, and so this is a sort of summary. It looks like the 2D case. You have now a region where the particle can either be moving in an erratic, chaotic fashion, or it can lock onto one of these helical spin states. So again, it's it's a nice development. The notion of when you go to 3D, you can get these helical spin states. So again, you can think of this as straight line motion of a particle with an intrinsic angular momentum. So we're looking to see how these states interact with forces and so forth now. Okay, so just to connect this to the Bohmian mechanics. So the old hydrodynamic interpretation of quantum mechanics was due to David Bohm. And so you take this, you take Schrodinger's equation, you apply the Madelung transformation, and this turns the, allows you to re-express Schrodinger's equation in the following form, and basically a hydrodynamic form. So these equations look very much like the shallow water equations in hydrodynamics. So rho now plays the role of fluid depth, and the quantum potential looks like a curvature term. So this in the shallow water, if you have a bump, then the surface tension acts to flatten it out. Likewise, h bar. So h bar is confined, note, to a single term, and that's the coefficient on this quantum potential. So the sort of new feature in this system, from a mechanics standpoint, is this quantum potential. Okay, and so again, this is it's just saying that you can think of the evolution of the statistics as prescribed by Schrodinger's equation as evolving in a sort of hydrodynamic sense. It's not telling you anything about the particle trajectories. This velocity here is the quantum velocity of probability, not the particle velocity. But what Bohm said is, well, let's say that the particle velocity is this quantum velocity of probability. If that's true, then you get the following trajectory equation. So you have the particle will then respond to the quantum potential as well as any classical potential that might be around. So for example, in the slit experiments, what they do is they solve Schrodinger's equation, from which they compute the quantum potential, and then they launch the particles over the associated quantum potential, and they get these trajectories. Okay, so this was, in my view, a very important step in that it restores realism, the notion of particle trajectories, to quantum theory. As we'll see, the shortcoming is it's non-local effectively, because it doesn't tell you where the wave function comes from, where this quantum potential comes from. So in any case, and it's also important as was a sort of counterexample of the impossibility proofs that held sway at the time. In fact, it motivated Bell to get involved in the problem. Okay, so, and there are certain features of Bohmian mechanics which we can also capture with the walking droplets. So these so-called surreal trajectories, so these authors proposed an interference experiment intended to expose the shortcomings of Bohmian mechanics. So this is our interferometer. We have a beam splitter here, 2 mirrors. So if there's only one mirror, then the photon will hit M2 and then just go in a straight line, and that's kind of what you expect. But if you put in another mirror here, it will actually, Bohmian mechanics says it will actually change direction at I. So this is the point of interference. There's no physical object there. And this prediction of Bohmian mechanics, they took offense to, and they said that that cannot be real, therefore they're surreal. And Aharonov and Weidman pointed out that, well, that depends on that depends on your physical intuition. So it's, again, they behave differently from what one would expect classically. And they actually did these experiments. So with weak measurement, you can get an idea of what the average trajectory is doing. And the average trajectories are indeed surreal. So they do have this strange change of direction. But their conclusion was that we demonstrate that the trajectories seem surreal only if one ignores their manifest non-locality. So they attribute them, Bohmian mechanics attributes them to non-local quantum potential, that is to say a potential of which is imposed by fiat. And here in the standard interpretation, they say, well, they're non-local, so therefore they're okay. So we see here that we can get analogous trajectories in our classical pilot wave system. So we have a geometry, basically the walls on either side act as the mirrors. And so if there's only one mirror, it will be deflected and move in a straight line. If you put in a second obstacle, so the situation is symmetric, then they will not cross the center line, so they're effectively surreal. So we can understand these surreal trajectories as a manifestation of non-Markovian pilot wave dynamics, and there's no need to invoke non-locality. Okay, and then so we actually go through there's this list of quantum mysteries, and so we try and work our way through it. One is this Weidmann Litzer-Weidmann bomb tester, and this is a sort of just a slight twist on the surreal trajectories, but basically in the absence of the bomb, particles, so we have again this interferometer set up with two mirrors here, beam splitters here and here. If there's no bomb, interference leads to the particle always arriving at D1. But if there's a bomb there, then the idea is that the notion is that the interference is disrupted, and so the particle is equally likely to go to D2 or D1. Okay, and so if the bomb is present 50% of the time, then 25% of the time it will go to D2. So you're basically detecting the presence of the bomb with a particle which never interacted with it. So it's called interaction-free measurement. So I was deeply confused by this until Valerie Frumkin, who is a postdoc in the lab, now professor at BU, connected this to the surreal trajectories, said, okay, let's now say that this chunk of this is like the second mirror, is our bomb, okay? So in the absence of the bomb, all particles go to the left. In the presence of the bomb, you can get these surreal trajectories. And so if the bomb is present 50% of the time, then 25% of the time you will have particles, you get these surreal trajectories. So you're basically detecting the presence of a bomb along a trajectory that never interacted directly with the bomb. Okay, so it's basically an analog of this bomb tester. Okay, so let's come back to Bohmian mechanics. Again, we've seen that it's important in restoring reality to quantum mechanics. Its shortcoming is, in my view, that it's non-local. So where does this quantum potential come from? Of course, our view is that it comes from the particle itself. And so he, in response to various criticisms, he said, okay, well, let's invoke a stochastic forcing from the subquantum realm. And this is only 2 years after his original paper. So he realized that it needed to be enriched in some fashion. So that's what he did. And notice it, so you can compare that model, which he developed with Vigier. So you basically have Bohmian mechanics, but augmented by this stochastic forcing. We compare it to our system, and we can basically decompose our wave force into the mean pilot wave, which we've seen and defined previously. And it's a non-local object in the sense that it depends on the statistics, right? But we know that the sum of that mean pilot wave and the perturbation wave field is just the real wave field. So we have something which is real and local. But it's interesting to connect our non-local mean pilot wave with the quantum potential, and then there's the stochastic forcing, which is basically ad hoc with our perturbation wave field. And of course, most importantly, we have our system is local, and we can rationalize the origins of the wave field through the particle vibration, whereas theirs is just imposed by fiat. So how do we get from our system to de Broglie? So de Broglie saw that also viewed the particle as the source of its pilot wave, and you get its frequency from this what Frank Wilczek calls a Pullman two line, so equals mc squared equals h bar omega. This defines the Compton frequency, and so particles then move in resonance with the guiding or pilot wave field. So we really imagine precisely this physical picture. Now the vibrations of the Compton frequency, the particle moves such that p equals h bar k, and then he suggested but didn't prove that the long-term statistical behavior would be consistent with the predictions of quantum theory. Okay, and so there's a map. I developed a map between de Broglie's mechanics and the Walker mechanics. Basically, the key parameter in quantum mechanics is h bar. In our system, it's surface tension. We've seen that the Faraday wavelength plays the role of the de Broglie wavelength. Okay, and so this is, of course, the million-dollar question. What is the matter wave in quantum mechanics? Bell himself said, we have no idea. De Broglie suggested that the field satisfies Klein-Gordon equation, so this governs the Higgs field and other relativistic fields. In stochastic electrodynamics, they suggested the electromagnetic quantum vacuum field, and others have suggested the gravitational waves, which I think would be a beautiful resolution of all this. So matter waves arise then in the fabric of space-time. So we now have computers, so you can kind of ask what this dynamics would look like if we projected it onto the equations of quantum mechanics. So if we take Klein-Gordon, this is perhaps what de Broglie would have done, and you put in forcing at the Compton frequency, and then you have a guidance equation. We just have the particle moving at a speed proportional to the gradient of the wave field. You get a pilot wave field, which basically looks like looks like a plane wave with a de Broglie wavelength. So it's different from the Walker. So you expect quantitatively different diffraction patterns, for example. And the key thing here is it allows you to understand where this comes from. So we had this on slide 2, P equals h bar k. Well, if a particle moves and is dressed by a monochromatic wave field, that means that the particle velocity is equal to the group velocity of its wave field. If those waves are solutions of the Klein-Gordon equation, then equating the two gives you P equals h bar k. Okay, and then there are more sophisticated classical pilot wave theories, which Dave Darrow in my group has been developing, and I won't go into details because we're running out of time. But you basically get wave fields which have both a signature of both the Compton wavelength and the de Broglie wavelength, and you get this sort of zitter when the particle interacts with boundaries, for example, in measurement settings, because its wave field is interfering with the surroundings, and we get actually a perfect match to the Fraunhofer diffraction pattern. So the system, which is alleged to be impossible to understand from a classical perspective, we can actually reproduce the result precisely. Okay, and so I'm running out of time. I have run out of time, haven't I? So let me just wrap up. Are you still with me?
Oh, quite definitely. Take your time.
Yeah, okay, good.
It's more important than time.
Okay, good. All right, you're still there. Okay, so right, and so the sort of basically the way we view things is we're trying to match, take de Broglie's physical picture as informed by the Walker system, and see what sort of dynamics we can come up with. And of course, the Bohmian people are, I would say, sympathetic, but they are deeply wed to the non-locality of quantum mechanics. So they see that as a shortcoming of our perspective. They say, well, you guys can't account for quantum non-locality, and our preference is to suggest that there is no such thing. So that's kind of the direction that we're going. And so, for example, again, they see non-locality in all of these systems. We don't see it in any of them. So let's a few examples here. Here they would say that this statistical wave you see top right is a complete description of reality. So if you look and observe and see a particle, that spatially extended object has collapsed instantaneously to a point. This is non-local. How can that be? There are many situations, including the double slit, where there appears, the influence of the second slit is seen as being a non-local interaction, so spooky action at a distance. And real surreal trajectories we've seen, they account for surreal trajectories by invoking quantum non-locality. So these are all systems where they infer, which they take as evidence of non-locality, and we see that one need not make such an invocation. Okay, and so of course the acid test are the Bell test. So if you've not seen Bell, I'm sure you've all seen Bell, so I won't need to go over it to too great an extent, but you're basically looking at correlations of particles which start from a common source and then are shot outwards, and you change measurement settings, and there's bounds on the extent to which these measurements can be correlated. So A and B or basically different measurement settings. And so the assumptions are realism, that is to say I didn't define that for this crowd, realism, locality, and measurement independence. So measurement independence is the one that people don't talk about too much, but it's the assumption that the hidden variables are independent of the measurement settings. And so the experimental violation of the inequality by Aspey's group is basically taken as proof of the impossibility of local hidden variable theories. Okay, and so we're looking at this with bouncing drops. This finally been published. So we basically have, instead of measuring plus or minus, we're measuring whether the particle's in the inner well or the outer well. So we have two subsystems. This is subsystem 1, subsystem 2. They are communicating through this coupling cavity, but they can't tunnel across into that cavity. So they can basically tunnel from right to left within their own subsystem, and they basically become correlated through the wave field. And so again, we simply measure. Yep.
I'm sorry, John, you have to change the slide, I think, because
are you there?
We're still seeing the Bell tests, the acid test of quantum. Oh, okay, that's
okay.
The new
You got it. Oh, sorry. Yeah, you got it now.
That's the strategic slide show. This
okay, so we're there. Can you see it now?
Yeah.
Okay, so we're again measuring whether they're in the inner cavity or the outer cavity, and the measurement setting is the depth of this wall, which prescribes the frequency of tunneling. Okay, and so again, you can imagine, because they have this coupling cavity, these things are talking to each other, so they can be correlated. They can become correlated, and they do. And we find that in a certain parameter space, you can actually violate Bell. But of course, in our system, the assumption of measurement independence is invalid. So the geometry of both cavities influences the hidden variable, which is the pilot wave, and therefore the probability of the outcomes in both cavities. So no mystery there, but still it's nice. I like this because I was always deeply confused. Just conceptualizing the Bell test was very difficult for me, but this is a way that you can conceptualize it, and you can now imagine how to separate the two subsystems. Of course, great efforts are made to separate the two subsystems in the quantum test. So here all we have to do is make sure that we basically have to start with drops together, send them outwards, and then close sesame here. So we close this wall, and so they're no longer talking to each other. Then we change the measurement setting. So that's how we're going to do a so-called dynamic test. And so the question is, can such violations survive isolation of the two subsystems? So there is a protocol, and we're working on this now, again, with Andre Nashbin. And there's reason. Let me just give you some reason, some green shoots of hope. This is a paper that Andre published a couple of years ago. So here he has two droplets. This is time in the vertical, and this is a horizontal position. So the drops are just moving back and forth in these cavities. And you can see here, they aren't talking to each other because we have this wall between them. And so you have low energy weakly correlated state. But if you yep.
It's another slide, right?
Oh. Let me see. Is we see that? What's the title? Towards the dynamic.
Towards the dynamic Bell test. Yeah.
Okay. Good. And so again, you have this low energy state where if they aren't communicating, if their waves are blocked by this wall, you have this low energy uncorrelated state. If you open up the coupling cavity, then you get the highly energetic correlated states. And you would think, okay, well, what happens now if we close these coupling cavities again? You expected you would go back to the dynamics on the left, but you don't. So basically, they have a memory of their initial interaction, and so this highly correlated state survives. And so, of course, the question is, might memory? So these are basically surviving by virtue of the memory system. So might memory account for entanglement? And I'll just give you guys, just to see if you were paying attention. Here's a little test for you. So this is two droplets. Have you guys, can you see the videos?
No, not yet.
Not yet. Okay, well let's just go out and back in. How about now?
Nope.
Damn.
Nothing.
You're not seeing anything or what?
No, we're seeing
Nothing.
towards the dynamic belt test from napkin.
Okay. I have to do a. I'm still seeing that one.
Yeah.
Maybe this slide. I have a big video in it. But in any case,
Okay.
Yeah, you can see it now.
Yeah. Now we can
Okay,
see
good.
it.
So basically, here we have so we have a geometry with two chambers, and here there's just one drop, and it just bounces in place. But if we put in a partner drop, then they start oscillating, right? They feel each other, and they become correlated. So the question is, what happens if we kill the lower drop? What's going to happen to the upper drop? It's surely going to go back to the way it was at far left. But in fact, it doesn't.
Oh.
So it actually stays in this dynamic state by virtue of its memory of its lost partner. So these are sort of illustrations of how memory can give rise to behavior which you wouldn't necessarily anticipate without familiarity with this system. Okay? All right, so that's all we have here. So basically, we have this hydrodynamic system, and it's a sort of wonderful vehicle for exploring the boundaries between classical and quantum mechanics, and it's extended the range of classical systems to include features thought to be peculiar to quantum systems, and can account for things which are typically attributed to quantum non-locality. And again, for me, it's important to sort of providing this conceptual framework, and it's a progressive approach, so we can sort of add to our list of quantum analogs. We've also seen that it's reminiscent of de Broglie's double solution theory and its modern extensions in stochastic electrodynamics. It really, for me, suggests the shortcomings of the quantum pilot wave theories, and it sort of motivated a new class of theoretical models. And so, for me at least, it suggests that the quantum paradoxes may ultimately be resolved through the elucidation of pilot wave dynamics on the Compton scale. And with that, I'll end and welcome any questions. Thank you.
Okay, thank you very much. What a wonderful presentation. Yeah, let me clap my hands, real time, real video. And so, yeah, excellent. So now it's time to, it's time to ask the audience for any questions about this. So go ahead. Any questions?
I have the infinite mirroring window, so I just saw an infinite number of hands go up, but I think I might have just done one.
Okay, super entanglement questioning. So, Professor Kroc, I think you have, Jose, I think you have a question. You're muted. Okay.
First, I want to thank John Bush for his very beautiful and interesting presentation. And this last slide was very, 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 very significant for me. Very significant for me. Things are correlated. Memory is always present. Past, present, and future are all interlinked. People seem to forget this, but it is always the same entity. And this last slide is very, very, very good. Thank you, John.
Thank you.
Okay, that was a wonderful statement. Any question? Okay, Flip, go ahead.
Thank you so much, Professor Bush, for your presentation. It's a brilliant presentation who give us one step to unify the different scales of this world. And in addition to the pilot wave theory, are there some aspects of the double solution theory of Louis de Broglie that also inspire your work? And in this sense, David Bond and Pierre Vigier proposed the concept of subquantum medium that de Broglie worked a lot, and Professor Kroc works a lot with the concept of subquantum medium. So, in this sense, can we call the fluid in your works in something like a macro quantum medium?
Absolutely. Yeah. I mean, this is what, one of the important things, as you go, this is quite different from what I used to do before. But having these sort of signposts along the way, for example, connecting to first de Broglie's mechanics, and so then the question is, of course, what is the subquantum medium? But then I connected to the stochastic electrodynamics community, and they have exactly the same physical picture, and their subquantum medium is an electromagnetic quantum vacuum, which is a bit strange because that's invoked, right, in many situations, like the ground state of the quantum harmonic oscillator. They invoke this, and you actually know the spectral form because of the work of Boyer. But it's not my job to say what this medium is, but certainly its role is being played by the interface, by the bath in our system, which serves as its memory.
Okay.
Thank you so much, Professor.
I have two questions, if I may. One is about, do you have any kind of Heisenberg uncertainty relations memory base for all these kind of phenomena?
Yes. So in that last the relativistic pilot wave theory that Dave Darrow developed, basically you see that if a particle is confined, so if you're trying to make a measurement, its pilot wave interacts with its environment, it starts zipping around, and it does so in such a way that is consistent with the uncertainty relation. So it's basically saying that these are an expression of uncertainty, which is an intrinsic part of a particle moving on a pilot wave, because you basically disrupt its pilot wave. And you can even, I remember, Couder even said this. He said, if you had intrusive measurement in the Walker system, if you could only see the Walker by having it pass through a pair of tweezers, those tweezers would upset its pilot wave and therefore deflect it. So you're basically changing its momentum by making a measurement. And of course, the beauty of the hydrodynamic system is that measurement is not intrusive, but that's not to say that you can't impose intrusive measurement on it. But yeah, so I would say that it is these uncertainty relations are a reflection, can be viewed as a reflection of the pilot wave dynamics. Even de Broglie discussed this.
Yeah, and may I add that most probably it has also to do with the memory limit, okay? Because I was thinking about uncertainty relations, more general ones where you have a tweak, a button in the memory, and so if you change the memory, you will have something nearer Heisenberg's and the usual quantum thing, and if you tweak on the other end, you will have something quite more deterministic or something. So
no, that's true. Yeah, exactly. Yeah. That's like, because turning off the memory is like turning off the pilot wave in some sense, right?
Okay, that would be the general idea. The other problem I see here, because I'm always seeing problems, as you well know, is that the entanglement problem needs to be addressed in terms of the speed of propagation of the signal, because of course we are absolutely in accord towards the thing that the two particles must be communicating through the wave, but the thing is at what speed. So if you have a limit speed, like the speed of light in the fluid, what I would be asking for would be an entanglement, a well-succeeded entanglement experiment at a super light or something speed. And I'm sure that I would say that I'm comfortable with the idea that, of course, there must be something communicating between the two particles, but at the same time, I think that the speed can be superior to the one imposed by light or something, according to the conditions within the memory, within the wave, within the reality. So I'm just throwing ideas at you.
The idea is that the memory short circuits the need for superluminal signaling, right? Basically you take these particles and you separate them, outside the light cone, and then we just put in a barrier. But the point is, the wave field, they're both dressed in a wave, and that wave is their memory, and it's a common memory because they started together. So the idea then is that these unexpected correlations are a result of the common memory of the two particles.
Okay, I think Olavo has raised his hand.
Paulo, Paulo, just before we pass to the next question, Professor Bush, may you stop the presentation just to give a full layout to the people on YouTube, please?
Yeah, sorry.
Okay.
There we go.
Oh,
How's that?
Oh,
There we go. There we go.
much better.
Sorry.
So, any question more? Oh, yes, Olavo. Go ahead, please.
Well, first, thank you, Professor Bush, for your presentation. It was very nice indeed. My question is, we are always interpreting Bohm's equation as a Newtonian equation with the addition of a quantum potential. And I stress this word, potential. But another possibility more consistent with stochastic mechanics, quantum mechanics, is to assume that Bohm's equation is an average Langevin equation, not a Newtonian equation, but a Langevin equation. In this sense, the quantum potential would not be a potential indeed, but the stochastic force that appears in the system. And in this sense, all the...
Uh-oh.
Oh, something got wrong with the wave memory field of Olavo.
We've been hacked by Copenhagen.
Oh yeah, Copenhagen that's affected. It figures. Okay, let's wait. And I think we can next go to Adam, because I'm
Okay, well, maybe I can come back to him later. Yeah, okay.
okay. What shall we do, Flip? Moving on. Oh,
Maybe
okay.
it's better.
Olavo.
Olav is back.
Ah,
Maybe. Oh, David Fries want to do one other question.
David has a question then. Okay. Oh, sorry. Let me try to manage this in Olav. Have you finished, because you freeze over there? Okay, Scott.
Well, I was saying that we are trying always to interpret quantum potential as really a physical potential, because we are seeing the Bohm's equation as an with
Oh, Olav, you.
Oh my God.
Okay, Olav.
Yeah, maybe I can just quickly comment. I know where he's going with this, and I agree. I mean,
okay,
the Bohmian trajectory equation shouldn't be considered as the trajectory of a single particle, because he's again equating the particle velocity with a quantum velocity probability. So if anything, it's some sort of ensemble average of velocities. And so then you do have a different interpretation for all of the terms. And again, I see it as a average, as a mean dynamics. And of course, the mean dynamics is going to be by construction consistent with the statistics. The point is, what are the real dynamics, of the individual particle? What is the trajectory equation for a single particle? And that I don't think he's addressed.
Okay, David. Go ahead. Thank you.
Yeah, can you hear me?
Oh, yeah.
Perfect. So let me see if I can sort my thinking through this, John. One of the things that I'm fundamentally, this is foundational, is think about patterns. In other words, structures and patterns. And you mentioned about pillars. Of course, I've actually done a lot of experiments, and I'm an experimentalist by first and foremost, but typically try to then create some underlying kind of reasoning or philosophy behind the experiment, right? So if you start to extend, let's say, the specific pillars in this case, there's a couple of questions I have. And if you don't mind me asking a couple of questions, I don't want to take a long time. When you start to extend this out spatially, whether it's, at a spatial X and Y or depth, right? You would expect that there's some correlation and coupling starts to happen from those structures itself, right? And so embedded in there almost is the fact that there's some memory built into the patterns, right? And so we anticipate that over time that a specific pattern can almost create a specific, it will create a specific field, a hydrodynamic field classically, but also that there are certain ways to be able to think about memory as something encoding at the beginning and then being able to amplify potential effects from the experiment. What's your thoughts on once you start to extend these pillars on out and engineer them into interesting, like structures?
Yeah, so the memory basically prescribes the, not only how long lived the waves are, but how long range in space the interactions with topography are. So for example, if you have something bouncing off a wall, it basically won't feel the wall until it gets to some critical distance, and then it will start slowing down. It'll start feeling the waves which are perturbed by the wall. And you can, in fact, in the Friedel oscillations, for example, you get Friedel oscillations off a wall. So there they go and they hit it, and then their speed varies as they ride over their wave field. And that's manifest in the statistics. So you get a statistical structure in the vicinity of the wall, but not far away from it. So it's basically, so again, the memory does indicate, does also prescribe sort of spatial range of structures in the system.
Good deal. And then the second question, have you all ever discussed about, so these are the hydrodynamic standing waves, right, induced by essentially acoustic, pressure. Have you ever had discussions around surface acoustic wave devices, which are quartz-based systems, right? And
yeah. In fact, I have a friend in Lille, Michael Baudouin, who's looking at acoustic pilot wave systems. So he's also a fluids person, but he's been looking at excitation of bubbles and trying to get them to self-propel, and he's been doing it both theoretically and experimentally. So I think because that's should be quite close to the 3D pilot wave theory. So you then have a particle oscillating and then again can become unstable and start self-propelling. So I think this be a very nice direction. I mean, the more pilot wave systems there are out there, the better our intuition about them will become.
Yeah, and then one last question. Sorry for this. I have the chance and I guess the honor of being able to actually ask these questions to to the panel. One of the things that I've been working on, if you look at space, right, whether it's connectivity or exchange particles, it's really, I look at this generally as communication between specific points, whether there's matter filled or not. And so if you take the communications, what we've been working on is, if you look at the convergence, most of my work is at the edge and in the real world. How do you create capabilities like communicate? I do robots, all kind of communication networks. When you look at I think this is my prediction in quantum, that quantum communications, both encryption and entanglement, generally, there's whole camps that basically do developments in those areas, whether it's QKD or, quantum entanglement, networks. However, that's typically encoded information. And so one of the things we're doing, and we see, or at least I see, the prediction is that we will ultimately, by inserting structures in either machines, which is what I focus on, so that you can create effects in the environment, that the convergence will be quantum and classical communications. In other words, create real, systems to operate resiliently in the environment. So to that end, one of the things that we're working on is ways to do classical communications that complements the quantum communications that has been expanding. And so one of the things we're doing is what I would call semantic networks. And that is by patterns, symbols, or semiotics. Like if I basically give you a sign, you almost know immediately, in human systems, we know what that means, right? And so underlying the semantics networks is meaning, right? And underlying that meaning, I think, is an intrinsic memory has to be part of that system. And so there's some interesting ways that I think quantum classical communications in real world that uses quantum in one case, but I've actually, started developing hardware that can start communicating with each other. We do machine vision, machine learning. So the two machines start to communicate with each other. Almost intrinsic in there, I think, is an underlying memory. Because if I do a semiotic or a symbol, there is similar to the entanglement or the wave function, there are multiple meanings at once. And I find that very intriguing because then there's an analog on that communications using information and ordered information. So I'd love to be able to kind of explore this a little bit more. One of the reasons why I was tickled pink, and thank you, Paulo, for being involved, allowing me to get involved with it, because I think it's a really interesting way that your memory kind of thinking about that, you know, captures entanglement. I think you see a similar thing in the meaning of language. You know, see at once meaning, superposition of different meanings at once. It depends upon what we then interpret or perceive that. So I'd love to be able to talk more about that. I think there's some really interesting implications on quantum classical communications using the hydrodynamic quantum analogs, but then also supplementing with some, you know, thoughts on how to communicate in real worlds using semiotics and, you know, semantics, because wrapped up in that is meaning.
Okay, thank you very much. Okay, thank you, John. Any words? Shall we pass? Okay, so perhaps we should now listen to Adam talk. Let me introduce him to just that the recording comes out very neatly and good. So Adam recently completed a postdoc in the mathematics department at MIT, as we saw working with John. He is the author again of the book Escape from Shadow Physics. And there's a subtitle, The Quest to End the Dark Ages of Quantum Theory. And this is an important thing. And I think it's only fair here to read a brief review about the book. The artfully written, splendid history of classical and quantum physics, this comes from Science, that rightfully highlights the limitations of current physics, Wall Street Journal says this, and argues for a revolutionary new understanding of quantum mechanics. So, here it is. So, Adam, you have the floor. Thank you.
Thank you all so much. It's really great to be here. Can you see the screen okay?
Oh, yeah, definitely.
Great. Okay. And let me know if there's any problems with the audio. Just feel free to interrupt me. But I'm just going to talk about some issues that are complementary to what John has discussed. Largely, I'm going to talk about kind of larger philosophical, historical issues and lay some groundwork for really kind of giving historical perspective and why one would take completely independent reasons for supporting the work that John has spearheaded for the past 15 years. So the other thing, just as a preparation to discuss, is that this book that you so kindly introduced, Paulo, thank you for that. It has a couple things. I mean, largely it was relatively straightforward to write, in the sense that I knew what I wanted to say, and I just needed to figure out the right way of saying it. But there were two things in particular that were very challenging and that took a long time for me to figure out. And I'm going to present one of them to you today because it underpins my treatment of quantum mechanics in the book. And it contextualizes, I think, the entire quantum debate and gives us a way of thinking about it. So it's a little bit of a misdirection at first because I'm not actually going to talk about quantum mechanics, at least to begin, or at least so it seems. So instead, I'm going to discuss the issue of heat. Can you guys see the slide? Okay, good. So we have this question, okay, what is heat? This is something that we know the answer to today, but back in the 1700s and the 1800s, they did not know. And it was quite a debate. And there were, in fact, two theories of heat. And one of them was called the vibrational theory, which states that heat is motion. And the other one was called the caloric theory, or it's also known as the material or the chemical theory of heat. And the interesting thing about this is that the caloric theory was much more dominant in the 17 and 1800s. So the vibrational theory was a minority theory, and pretty much everybody universally believed that heat was this thing called caloric, which is it was imagined as an extremely light, invisible, perhaps weightless form of matter, material that permeated other matter and attracted or to differing types of matter with a different affinity, and also self-repelled. So this is a screenshot from a couple different sources of ancient, not that ancient, but early scientific texts. So on the right we have this thing by Lavoisier, who presented, he helped revolutionize chemistry. He named hydrogen and oxygen. Real quick, John, could you mute yourself? Because I'm getting feedback from my own voice, I think. Thanks. Cheers. And here, we have a book. It says these are the modern discoveries, and the beginning of this book, chapter 1, it begins with the combinations of caloric. So the most important thing to talk about in chemistry in 1790 was caloric, and then here on the left we actually have some diagrams from a book by John Dalton, who was one of the first people to imagine that there might be such thing as molecules that came together in different ways, and you could rationalize the states of matter based on the properties of these kind of different combinations of atoms or some sorts of elements like this. And these rays that are going out are for him the actual aura of caloric that is associated with the different types of matter, and the sizes of these boxes represent kind of the strength of the caloric aura around them. Okay, so the point of this is that there were two theories of heat back in the late 1700s, early 1800s, and even more importantly, the wrong one was dominant. So in fact, it was better developed. The theory of caloric was more fully developed. It was more mathematically developed, and it actually helped people to make genuine scientific advances. So using the idea of caloric, Laplace solved an old problem that defeated almost everybody else previously, including Newton, relating to the speed of sound in air. As here, and you can see on the left already, I mentioned John Dalton's work that helped him develop a actually correct idea. And the theory of vibration, it had its supporters, it had some interesting results, but it was harder to develop, and it didn't really go anywhere for a long time. So that's the first point that I want to highlight about the history of thermodynamics. Okay, the second one is this. There was a heat equation. This is in 1804 or 1805 when it was first discovered by Fourier, and it was in 1820, I think it was, he published his big book on heat, and it was essentially just a large multi-hundred-page exposition on the heat equation. It didn't really talk about what heat was. He didn't need to talk about what heat was. He just talked about the math and how the equation worked. So this is interesting. Back in Fourier's time, they had an equation to describe the evolution of heat, but they didn't know what heat was. They had two different theories for the nature of heat. Okay, so now we get to another really interesting aspect of the history of thermodynamics, which has to do with positivism. So this is Auguste Comte. He's the first philosopher of science, probably, that we would recognize. And he started a philosophy called positivism, which held a lot of things, but the main thing that it believed was that there was an evolution of knowledge from more primitive, more wrong types of knowledge to more advanced and more correct types of knowledge. And there were three main stages. The first stage was theological or superstitious. And in this stage, according to Comte. People saw the wills of divine entities behind everything, and you know, the planets moved because literal angels pushed them along in their crystalline spheres, and you know, God made things happen for reasons that we might be able to figure out. After that, knowledge evolves to the philosophical stage, which is about discussion, disputation, and kind of thinking up concepts that you can use to explain what you see and trying to fit those concepts together into a philosophical framework. At which point, if you can get all the concepts to fit together, you say that you have understood things. And this he associated with just disputation, discussion, speculation, and metaphysics. So the metaphysics for him was a transitional stage from the theological way of thinking about things to the positive, superior way of thinking about things, which for him was it's essentially empirical mathematics. He considered it to be the mature, correct stage of knowledge. And what you do is you stop talking about the hidden nature of heat and the hidden nature of anything. What is gravity really? What is time really? For him, these were discussions that have no purpose, no point. They were completely empty. And instead, what you do is you observe, you look at things, and you come up with the mathematical laws that explain what you have observed. So here we have the first line of Fourier's book on heat. And Fourier, this is essentially like a one-line manifesto of positivism. There's like primary causes, the essences, like what is heat really? They're not at all known to us. But they are subject to simple and constant laws, which we may discover by observation, and the study of which is the object of natural philosophy. And Comte loved this. So he was a friend with Fourier. He dedicated his great work on positivism to Fourier, and he never missed an opportunity to praise Fourier. So he mentioned Newton's theory of gravitation as an example of positivist kind of knowledge. And his second example, you know, looking for another example, he came up with Fourier's heat equation. And this is a quote from the book, which itself is a quote from Comte, where he says, talking about positivism, to elucidate it, I will choose the beautiful series of researches by Monsieur Fourier on the theory of heat. In this work, which is so eminently positive in its philosophical character, the most important and most precise laws of thermology find themselves unveiled, without the author inquiring one single time into the hidden nature of heat, without him mentioning, except to indicate emptiness, this so agitated controversy between the partisans of the material caloric and those who made heat consist in vibrations. So for Comte, attempting to approach the primary causes with hypotheses about what might really be going on it would result in interminable discussions. And it's an attempt to make pronouncements on, and Comte really believe this, on questions that are necessarily insoluble for our intelligence. So this is a very strong, a very interesting claim about like the boundaries of human capabilities in terms of cognizing nature. And he made a lot of predictions based on this idea that there are limitations. And I'll just go over some of them, right? So planetary astronomers, this is again a quote from the book, would be amused to learn that their entire field was declared impossible by the armchair musings of this 19th century philosopher. Concerning the possibility of measuring the temperature of the planets in our solar system, Comte said that this order of facts is forever excluded from our recognition. We can never learn anything about the internal constitution, the heat absorbed by their atmosphere, or anything about the chemical or mineralogical structure. Similarly, he thought we could never learn anything about the chemical compositions of stars, a claim that has been called Comte's blunder not too long ago by a different scientist. When it came to biology, he blundered again, thinking about inorganic and organic matter, Comte said that there is no need to ask if the two classes of bodies are or are not of the same nature. That is an insoluble question. Embryology was also considered insoluble by Comte, who pronounced research into the physiological generation and development of animals to be an insoluble inquiry. These are all quotes. And I could continue, but he also, I think relative to us, the more interesting thing he said is he also commented on the particle wave duality, which by then was a long-standing historical back and forth having to do with the nature of light. And he said that both the particle and the wave picture were chimerical hypotheses, and that supporting one or the other on the nature of light was just a vicious method of philosophizing, and that these hypotheses only obscure scientific reality. Okay, so this is positivism. I think probably many of you are already familiar with it, but this is the beginning of positivism. And it's interesting that it's so closely connected with the heat equation. So let's go on. Okay, so Comte was wrong, totally wrong, about the nature of heat and all these other things that he said we could never know anything about. In fact, we know now that heat is mean molecular kinetic energy. And Maxwell, Boltzmann, Gibbs, the people who established statistical mechanics and put thermodynamics and the nature of heat on a solid foundation. And in particular, this work led to the correct interpretation of the heat equation as a diffusion equation. So we think about anything that has a temperature, like the air, like a bar of iron, as being composed of endless, inconceivably many number of small particles of matter that are constantly colliding and interacting and vibrating. And their interactions can be modeled as collisions. And then anything that operates similarly, like with a large number of collisions, can be described with the heat equation. So it's a diffusion equation. And so we have things like the diffusion of mass, which Fick wrote about in 1855, the diffusion of prices, which Bachelier wrote about in the 1900s, and the heat equation also describes the flow of blood through capillaries, neutrons through graphite, and lots of other things. So Comte was totally wrong. Heat is statistical. So part of the reason that it was hard to come up with the nature of the heat is because it was statistical. So we needed to think on a different level. We needed to understand the dynamics underlying the actual large scale averaging out, which is what heat is. Okay, so finally, let's move on. So now we're going to go to quantum mechanics. And here we go. Here we have Schrodinger, and we have this thing called the Schrodinger equation. And I'm going to write it here, but first I'm going to play a little joke on you, because that is not the Schrodinger equation. This is the heat equation. We already looked at it. So actually, let's look at the Schrodinger equation. How do we need to change the heat equation? There we go. Okay, so the Schrodinger equation and the heat equation are very interestingly close to each other. So this is one of the first, this isn't a discovery. This is relatively well known. But this is one of the first kind of parallels we have between thermodynamics and quantum mechanics. Let's go on. What else can we find? Well, this slide, I always have to remind myself what this is supposed to mean, but it's meant to kind of indicate the broad number of interpretations that we have in quantum theory. There are a lot of them. We know that. In the counterculture in the 60s and 70s made a big deal out of the von Neumann-Wigner interpretation of quantum mechanics, which was that the human consciousness collapses the wave function. So people thought that this was proving psychic phenomena. And there's a whole, probably the most well-known interpretation for the general public is this one, because of books like The Dancing Wooly Masters and that kind of thing. We also have on the right, we have like multitude of planets, which is meant to signify the many worlds interpretation. And this interpretation, anytime a quantum event happens, there splits away a universe where it didn't happen. So you have the particle going through one slit versus another slit. It happens in different universes. So these different universes are actually somehow interfering with each other. And you just have an enormous multitude of universes. And there are many people who believe that this one is the correct interpretation. It's far more popular than the psychic one. And then here on the left, we have Niels Bohr's coat of arms. He won an award it's called the Order of the Elephant. That's why there's an elephant down at the bottom of his coat of arms. And the interesting thing, they give you a huge elephant, and you have to wear it around your neck when you go to parties. And then when you die, you have to give it back to the queen. But one of the things that you get when being inducted into this order is you get your coat of arms, and you get to put it up on Frederiksborg Castle. So Niels Bohr had to make a coat of arms, and this is what he made, which is you have this yin yang, meaning symbolizes opposites being in harmony, and then his Latin motto is contraria sunt complementa, which means contraries are complementary. So this is the Copenhagen interpretation. This is another interpretation of quantum mechanics. Okay, so the point is relatively clear. We have many interpretations of quantum mechanics. So now let's go to another parallel that is kind of understood, at least by the philosophers and historians of quantum mechanics, which is that the early quantum theory, and especially the Copenhagen interpretation, are very strongly positivistic. And this started with, I think it was maybe in the air a little bit, but Heisenberg's the first line of his first paper after he had his epiphany on this little island, and he spelled out matrix mechanics, is this quote here: "The objective of this work is to lay the foundations for a theory of quantum mechanics based exclusively on relations between quantities that are in principle observable." So this is very similar to Comte, because positivists say things like this. They say that, well, it's not in principle, it's not observable even in principle. So it has no role to play in the theory. We shouldn't even discuss it. And this is what Comte said. The hidden nature of heat is in principle unobservable. And similarly for Mach, if you guys know about him, he denied the existence of atoms. For him, they were in principle unobservable, which we know now is wrong, because, well, John showed a picture of atoms, like an actual picture of atoms, where they drag them onto a substrate and arrange them in a circle. So I'll read you a short quote from this about the positivism in the Copenhagen interpretation. So these early positivistic spasms, like this one from Heisenberg, they could have been a passing thing, but they were not. From this beginning, denial of hidden natures attended the quantum theory with an uncanny intimacy. Consider the following quote by Bohr. He wrote in 1929 that in our description of nature, the purpose is not to disclose the real essence of phenomena, but only to track down as far as possible the relations between the manifold aspects of our experience. It was positivism as a philosophy was so pronounced in the early days because Bohr and his followers believed that quantum theory forces us to make a renunciation. And this is a similar idea to what Comte said. Comte said that true knowledge begins with the renunciation of the search for hidden essences or primary causes. So they went on about this, and I won't go into it too much. Actually, I think it's relatively clear. But this is one of the major sticking points in the early debates on quantum mechanics. It was about this idea of positivism, and Einstein pushed back against it. Even though in his early days, Einstein became relatively famous for making a positivistic move with special relativity, in the end, he decided it wasn't a legitimate move. And he argued with Heisenberg about this. He thought that Heisenberg's positivistic intuitions were going to get him into hot water. And so, I mean, there's more to support this connection between early quantum mechanics and the quantum orthodoxy and positivism, but it's relatively well understood. So we can move on. And then finally, I will play this little movie. Hopefully you guys can see it, but maybe I can't play it. Let's see. Oh, I know why. 1 second. Nope. Well, oh, there we go. Okay. Okay. Yeah. Sorry. So this is these are the first 3 states of a quantum harmonic oscillator. On the left side, you have the 2 different solutions of the wave function, or the real and the imaginary parts, and on the right, you have the transformation of the wave function after you apply the Born rule, which gives you a probability distribution. So quantum mechanics, as we know, is statistical. It's a statistical theory. It doesn't talk about any underlying dynamics, such thing as a trajectory. You don't speak of the state of the particle until you've measured it. And when you make many, many measurements, you wind up recovering a probability distribution. So let's move on. Now we can talk about the parallels, and we can list them all. Okay, so between thermodynamics and quantum mechanics, we have a lot of similarities. So there were multiple interpretations of the nature of heat, just as there are multiple interpretations of quantum mechanics. Positivists explicitly denied the hidden variables would ever be found to explain the heat equation, just as they did in the 20th century and today in quantum theory. Both theories are statistical, and the heat equation and the Schrodinger equation are extremely close. They differ only by a factor of I. Okay, so this is kind of like this is a big part of the book, but it's relatively simple to explain and discuss. I think that these parallels should be more widely known. So another thing, I think, moving on a little bit, discussing the debate, Bohr-Einstein debate, and really how these things came to a head. It's really about this issue of whether or not we will discover a underlying dynamics to the quantum theory. And in a sense, it's interesting to point out the thermodynamic parallels because history is kind of repeating itself. Bohr and the Copenhagen philosophy, they deny that there is a relationship between an underlying deterministic dynamics and what we see in the quantum predictions and to get the probability distribution. And as we know, Einstein disagreed pretty strongly, and they debated it back and forth inconclusively. Although the general consensus is that Bohr won that debate. So I think another interesting thing I came to in the book is a philosophical realization that this denial of underlying causes is essentially a denial of the principle of sufficient reason. The principle of sufficient reason is a very fundamental aspect of the scientific mode of thinking. And essentially it states that everything that happens has a cause. If something happens, there's a reason it happened, and you may not be able to observe it, but there's still a reason that it happened. And the scientific mode of thinking attempts to find those causes, understand them, rationalize them in order to understand exactly how something happened. So if we deny the principle of sufficient reason in any area, then there is no cause for the effects that we see. So I think that this is I think that this is kind of the heart of the issue here, at least philosophically. So I want to read you the end of the chapter where I discuss these issues. In formal logic, when you try to deduce something from a falsehood, you can get anything at all to be true. This has the coolest possible name, the principle of explosion. Assuming a falsehood to be true means that you will never be able to discover an internal logical contradiction in the subsequent chain of reasoning. You allowed a false proposition through the door, and like some kind of demon worm, it gave you infinite wiggle room. In particular, you will no longer be able to make the reductio ad absurdum argument, which introduces assumptions and then derives a contradiction to disprove one of the assumptions. Something similar to logical explosion seems to have happened in quantum foundations. From the identical starting point of quantum completeness, which is this idea that there is no underlying dynamics, the various interpretations wind up in different places so outlandish that they would seem to be self-refuting. But we cannot actually refute them because no contradiction can be obtained. Reductio ad absurdum arguments only work if two people share a sacred truth. Anything that contradicts that truth is then absurd. Such arguments are used all the time in mathematics. If a chain of pristine reasoning ends with the statement that 2 + 2 = 5, then at least one of the assumptions that started the chain is wrong. Mathematicians take this as definitive. But this is a cultural norm as much as a logical one. We could easily imagine a society so intellectually decadent, so married to a false assumption, that a proof ending in 2 + 2 = 5 was not a reductio for them, but instead a profound realization about how mathematics is much richer than previously thought. How mind-blowing. Scholars could spend their careers spelling out the nature of this new mathematics in which all numbers are actually equivalent in some deep sense, and what was previously considered impossible is actually true. What other things follow from 2 + 2 = 5? Do we have the courage to accept them? This is roughly the stage we are at with quantum foundations. The moment physics denied the principle of sufficient reason, it let falsehood through the door. Physics stopped thinking seriously about the actual problem. Now, and this is a quote from earlier in the chapter by Sabina Hossenfelder, now they produce mindless mathematical fiction. There are no reductio ad absurdum arguments anymore, because absurdity is a matter of taste, and there is no arguing about taste. When trying to understand Schrodinger's equation these days, the only constraint is mathematical consistency. The interpretation just needs to be logically possible. Unfortunately, when we take every logical possibility seriously, we debase our physical intuition. It becomes increasingly difficult to talk to each other as our pictures of the cosmos diverge. And then I say, oh yes, this is basically the problem is what I said, the denial of the principle of sufficient reason. You simply cannot do science without assuming there are causal explanations. Such a faith is non-negotiable. As Jaynes put it, there is clearly a major, fundamentally important mystery still to be cleared up here, but unless you maintain your faith that there is a rational explanation, you will never find that explanation. And in a letter to his friend Maurice Solovine, Einstein expressed his faith in the principle this way: I have no better expression than religious for confidence in the rational nature of reality insofar as it is accessible to human reason. Wherever this feeling is absent, science degenerates into uninspired empiricism. So this is kind of, these are the stakes. And I think that I will start to conclude with a few kind of broader observations and then a few quotes, some of my favorite quotes from the book. So really, what we take away from this, if we want to actually learn from history and learn from the history of thermodynamics in particular, is that there must be an underlying dynamics to quantum observations of the quantum theory. There must be a reason that things happen the way they do. And the best idea we have so far is really the only viable hidden variable theory, which is de Broglie's theory from all the way back in 1925. There is really no other hidden variable theory. And as we know, as John's discussed already, de Broglie's ideas are extremely close to this hydrodynamic quantum analog work that has been discussed for decades now. And it's just very, I think, suggestive that de Broglie had these ideas. He made a fundamental contribution to quantum mechanics in his doctoral thesis based on these ideas. And then these ideas were discovered again by David Bohm in 1952. And then now they have been discovered again in 2005 in Paris. And these probably it's probably not a coincidence. It's probably not a red herring or a false lead. The thing that happened to de Broglie is that he prepared these ideas. He had written a paper called the structure, I think it was the nature of radiation and the structure of matter, something like this. In 1927, it was published. Shortly after it was published, electron diffraction through crystals was observed. And in this paper, he talks about the double solution theory, which has been mentioned already in this conference. And he imagined essentially a particle oscillating with some vibration in sync with an ambient wave field. The ambient wave field was a material wave, and it pushed the particle wave around. And then when there were multiple particles, they entered into strongly nonlinear interactions, which de Broglie himself really couldn't rationalize. There weren't computers back then. And he felt himself, as he admitted, unable to resolve these mathematical difficulties. So he got invited in 1927 to the Solvay conference, which is this famous picture, probably the most famous conference proceedings picture ever. And he had a problem because he didn't really know how to discuss his ideas. The mathematics he couldn't really justify. So what he did is he adopted a point of view that was really added as an appendix in his 1927 paper, which is called the pilot wave theory. It's not the double solution. What he imagined in the pilot wave theory is, well, you just assume that there is a wave and you assume that there's a particle and they kind of push each other around and you get the statistics. But he said that this is not really, it's not really satisfying. And he didn't understand at the time by adopting this position, he had adopting this idea and not talking about the underlying physical intuitions or motivating concepts, he had greatly weakened his own position. He came to the conference and hardly anybody really supported him. He got a lot of criticism from Pauli, which he didn't really feel like he could answer. And the only person that supported him was Einstein. And Einstein came up with actually a very penetrating thought experiment, which wound up being the basis of his 1932, I think, paper with Podolsky and Rosen that everybody knows about, that's advanced the foundations of quantum mechanics so much. And nevertheless, Einstein's support wasn't really sufficient for Double, and he stopped. So this leads me to this quote by Sabine Hassenfelder, which I think is quite good. She wrote, "In the past decades, physicists have not succeeded in solving any of the open problems in the foundations of their field. Indeed, it's not even clear we are getting closer to solving them. In this situation, it makes sense to go back and look for the path we did not take, the wrong turn we made early on that led into this seeming dead end. The turn we did not take is resolving the shortcomings of quantum mechanics." And I would submit that the real moment that things went off the rails in the wrong direction was here at this conference, when Du Bois didn't really get enough support for his ideas. So finally, I'm going to end with some of my favorite quotes from the book. John's laughing, he knows what I'm about to say. This is one of my favorite academics of the last generation, Edwin James. He's pretty well known, really a great guy, very smart, and he did not pull his punches. So I'm going to read, they're really his main quotes, like most of the quotes in the book. So the first one is this: "All these years it has seemed obvious to me, as it did to Einstein and Schrödinger, that the Copenhagen interpretation is a mass of contradictions and irrationality, and that while the theoretical physicists can, of course, continue to make progress in the mathematical details and computational techniques, there is no hope of any further progress in our basic understanding of nature until this conceptual mess is cleared up." So then moving on to the next quote. This is his diagnosis of the state of quantum foundations and quantum theory, which is, you can find in his book Probability Theory, which is a outstanding textbook on Bayesian probability. "In current quantum theory, probabilities express our own ignorance due to our failure to search for the real causes of physical phenomena, and worse, our failure even to think seriously about the problem. This ignorance may be unavoidable in practice, but in our present state of knowledge, we do not know whether it is unavoidable in principle. The central dogma simply asserts this and draws the conclusion that belief in causes and searching for them is philosophically naive. If everybody accepted this and abided by it, no further advances in understanding of physical law would ever be made. But it seems to us that this attitude places a premium on stupidity. To lack the ingenuity to think of a rational physical explanation is to support the supernatural view." And finally, this is probably my favorite quote in the entire book. He wrote, "In biology or medicine, if we note that an effect does not occur unless a condition is present, it seems natural to infer that the condition is a necessary causative agent for the effect. But suppose that condition does not always lead to the effect. What further inference should a scientist draw? At this point, the reasoning formats of biology and quantum theory diverge sharply. In the biological sciences, one takes it for granted that in addition to the condition, there must be some other causative factor not yet identified. One searches for it, tracking down the assumed cause by a process of elimination of possibilities that is sometimes extremely tedious. But persistence pays off over and over again. Most enzymes, vitamins, viruses, and other biologically active substances owe their discovery to this reasoning process. What is done in quantum theory today is just the opposite. When no cause is apparent, one simply postulates that no cause exists. Ergo, the laws of physics are indeterministic and can be expressed only in probability form. Biologists have a mechanistic picture of the world because, being trained to believe in causes, they continue to use the full power of their brains to search for them, and so they find them. Quantum physicists have only probability laws because for 2 generations we have been indoctrinated not to believe in causes, and so we have stopped looking for them. Indeed, any attempt to search for the causes of microphenomena is met with scorn and a charge of professional incompetence and obsolete mechanistic materialism. So that's James. Just outstanding, I think. Finally, I guess that's actually it. I wanted to end there, and thank you all so much for listening. And pretty much everything I took from here, I think I've encapsulated the core, some of the core message. So thank you very much.
Okay, thank you. Excellent talk. Excellent talk. Yeah. Any questions for Adam? Oh, Professor Crocker, go ahead.
Yes, I enjoy your presentation, and I think you put a very interesting point. But in science, it's always hard to change from classical physics, where people want to be certain about things, to live in uncertainty, it's very complex. And quantum mechanics put us before a world that is much more complex. And you cannot say what happens. The most you can say, establish probabilities for the happening, nothing more. And later you have to make a bet what happens following. And quantum mechanics put just this position. This is a break in the certainty of physics. When you have a book of physics, this equation rules phenomena. The equation is a human construct. How can a human construct rule nature? The human construct, the most it can do is describe in certain conditions, certain aspects of the behavior of nature, nothing more. Our form does not rule nature. So the so-called universal constant. Who believes really that we human beings were able to determine things that remain constant forever? It's not possible. I think you put a finger just in this point. It's very interesting, all work in this. And I think that John Bush gave a great contribution to open a window for all the physicists and all the people to try to go a little beyond. Because, as you know, De Broglie was an heretic. All physics that does not agree with orthodox quantum mechanics are heretic. And to break this barrier, it's not easy. And I think John Bush, and I am very grateful for, to help to break this barrier, to show that there are other possibilities to look, so that every people understand if they look a little more carefully. So I want to thank you for your work. Thank you.
I think Adam's book also breaks one or two or maybe more barriers, as he put it. But David has a question. Go ahead, David.
Yeah, I have 2 questions, if you don't mind. So the one, for Adam, when you look at the primary causes and the history, so there's mathematical formulations of, for instance, quantum mechanics has been the traditional trajectory or arc to be able to then probe into the reality or underlying reality. So mathematical formulations. Then we moved into observation, and you brought up Comte. And if you know, just as an interesting sidebar, if you notice, like American Indians or Native American Indian science was all based on observation, no underlying formulation. So it's interesting. They would look at patterns and try to do prediction based on that. So it's kind of, so now you move from mathematical formulation approaches to observation. And now we're in kind of this new phase of data science, which is in many cases machine observations, right? If you look into the crystal ball, what's your sense as we move in this kind of fundamental kind of observational strategy using machines and creating data science and coming up with formulations? Are we going to move into this space of uninspired empiricism like you were talking about?
All right, so this is a super interesting question. Thanks for that. I don't have a definitive answer, but what you're reminding me of is what Chomsky said about this, which I tend to agree with. Okay, so he's a pretty strong rationalist, and he pointed out that actually the machine learning paradigms that we have today are kind of providing false promise. And the reason that the suggestion that he made is like, imagine that you go into your physics department and you put your camera out the window, observing the world in the quad for years, right? You're going to generate an enormous amount of empirical evidence, tons of data, and then you can have the computer, kind of wash through it all and try to find the patterns. But it's not going to discover, for example, anything even remotely like what Galileo was managed to formulate, right? It's not going to get like harmonic motion. It won't get the Newton's laws of motion, and the way that science has operated, at least up to not too long ago, is to simplify things, is to forget about all of the stuff that doesn't matter, and to try to formulate an actual law that explains the simplified situation. Like everything always works that way. You always have to abstract away things that don't matter. So I think that it's likely that that's correct. I don't think there's a replacement for actual understanding. And despite the evident power of neural networks and machine learning to generate what's the right way of putting this? I think what they do is they distill pre-existing understanding and all of the work that humans have already done, right? And they also have misunderstanding, and they include that as well. So that's my feeling.
Excellent. Very good. Thank you. And then the second question is related to the book. And so using this particle wave field coupling, in a sense, you've injected with your book a particle into the physics or science field. Now that you've actually had that book out there, and dependent upon the reactions and the sales, which is data, what's your sense in terms of its like impact? Is there kind of a recoil from folks out there, or is there acceptance or moving the needle? What's your sense?
Was it a high memory or low memory
impact? Yeah, right.
Yeah, totally. So I think that most of the people involved in the book, my editors and myself included, were expecting physicists to be angry, expecting more people to just yell about it all, right? And for there to be a kind of a very, maybe even acrimonious public debate at points. In fact, I think that hasn't happened hardly at all. And I think that most physicists, there's a couple of reasons, but most working physicists don't work in foundations. And the people who do work in foundations, they are really just so far down like a different road that an intervention like this, the particle, as you say, has not that much of an effect on them, right? And I think that pretty much all of quantum foundations is involving itself with things like Bell's theorem, or the many worlds theory, like how quickly does the universe split, you know, like that kind of thing. And so it's interesting. Almost all of the reviews were very positive. Scientists reviewed it very positively, and so I think that it's also the case that the field is more open than people tend to think. We have this impression that you know, the people here in this group and other people who believe similar things to us are like the embattled minority. And I think it was clear we are in a minority, but I think that other scientists are maybe more open-minded than we tend to assume, but they're not going to work in this area. They don't think they can make progress or whatever. And there's no real, there's no alternative for them to grab onto and you know, take a stance on. So I think that if we can provide that, which has been an incremental project that has largely been driven by John at MIT, then it will start to become more and more of an accepted position among scientists.
Yeah, the nice thing about the subject is it's sort of a platform for exploring quantum foundational issues from a very safe space, which is fluid dynamics. You know, if somebody gets really angry, it's, oh, it's just fluid dynamics. But
It's just fluid dynamics. Just droplets.
But that's what happens. I mean, even in the review process, right? I mean, we just went through, you know, the review process for the Bell paper, and, you know, basically physicists just triggered them, and so they got super angry. It's like, okay, fine. Well, it's fluid dynamics, so we published it in a fluids journal, right? And, you know, maybe the fluid dynamicists are going to understand things, I think, sooner than the physicists. But on a positive note, I have noticed younger people are much more accepting, because, I mean, you all remember your reaction the first time you took quantum mechanics, and you sort of fed this line about, you know, you can never understand it, don't even try. And this is frustrating. I mean, this is anti-scientific. This is what set me off as a student. And a lot, you know, if you can talk to someone who's just gone through that and say, actually, here's a way of looking at it, and they get excited. And we've got a number of crossovers from physics now, physicists working with us, and there are a number of postdocs, and they just, you know, they come and pitch their idea to the group, and they say, okay, we want you to try and do the Josephson junction. We want you to try and do a transmon. And so we sort of learn these things, and they bring a fresh perspective, and they're open-minded. I mean, I think the older generation was more embattled and less. They didn't have the nice thing about this is something concrete to hold on to, right? You can really say, okay, what can we do with this system, with this perspective? So I think things are moving in the right direction.
Okay. May I add that perhaps one should have a scientific journal on pilot wave theories? I think that would kind of help the young people and some of the old also to publish without any problems. The other thing I wanted to ask Adam is, do you think that with all this business of quantum computation, someone will kind of stumble in let's say, an empty wave or a kind of strange phenomena going on, or someone would dare to make a quantum wave detection or something, which I think it's a very important game changer in all this. What's your thought about this?
I don't expect this to happen in quantum computation. I feel like if it was going to, I feel like people looking for it explicitly makes it more likely,
okay,
you know, to be seen or not seen, right? That said, though, I don't really know that much about quantum computation. I only have like some vague intuitions about it. So, you know, I don't really know.
Okay. Yeah. So, Flip, do you have anything to add? Or? Oh, okay.
I want to do one question to Dr. Adam Kay. Thank you so much for your presentation. I love the name of your book, Escape from Shadow Physics, and you have a different kind of writing too. It's a poetic and strong writing they understand me. And the book, in this year, the group, congratulations for you all, because you did 2 great publications. The advances in pilot wave theory and the escape from shadow physics. So it's a really important year with these two publications. And I want to insist in my question, I want to insist in the comment of Paulo Castro to John Bush, but now I want to know what Adam Kay think about the limit of the speed of light. The limit of speed of light don't leave us in a kind of shadow physics until now.
So you're asking what I think about the limit of the speed of light?
Yeah. What you think about the limit of the speed of light? It's a limit of our theories, of maybe a limit of the universe. I am an astronomer, and I don't believe in this limit of the universe.
So everyone takes their best guess at this point. I think that it's the case that still the foundation of special relativity contains a profound mystery, because you can rationalize the observations by Einstein's 2 postulates. And one of them makes sense, that the laws of nature should be identical in all inertial reference frames. But the other one is very weird. So like, why should the speed of light be constant in all inertial reference frames? That's extremely strange. And I don't think that anyone has succeeded in explaining that, or even start. I think they stopped trying. Actually, it's just become the postulate, and now it explains everything. So, and then it creates this existence, like the Minkowski space-time formulation. And now we understand we can do things about light cones, and light cones bend in different reference frames. And now, now we have general relativity. Oh, okay, now we have quantum mechanics, and just the world just keeps getting stranger and stranger. So, in my personal opinion, I think that it's highly suggestive that there is a wave speed, a maximum wave speed to the universe. And if you look in the history of the debate about light, which I discuss a little bit in the book, people went back and forth about whether light was a particle or a wave. So Newton said that it was a particle. Hooke and Huygens said that it was a wave. Young said it was a wave. And Fresnel said it was a wave. And one of the reasons that Fresnel said it was a wave is that the speed of light was constant. Whereas if it was a particle, it should have all different kinds of speeds. This is just how you can have all different kinds of speeds of any kind of matter. And that was a guiding principle for him. And the idea is that, well, waves travel through media. And the medium, the properties of the medium, is what determines the wave, right? So the wave speed, right? And that's the way it is in air, in water. And the weird thing is that it didn't work the way that people expected it to work in light. They just thought, okay, we're going to find the ether. We're going to figure out the dynamical, properties of the ether, and then case closed. But they just couldn't figure it out. And ultimately, because of stellar aberration, because of all these, like the inability, Michelson-Morley effect, the inability to find any difference in any reference frame for the speed of light, right? They gave up, and they said that there is no luminiferous ether. There is no medium for light, right? So that's kind of where we're at, actually, still today, is that we don't understand why the speed of light should be constant in all inertial reference frames. Einstein, even though his special relativity, this was the positivistic move I referred to, but I made Einstein famous. He denied the existence of the ether because it could never be observed, right? And everyone was like, oh, what an amazing advance. Now Einstein's famous. And then Einstein he actually changed his mind. He basically said that the idea of the ether is simply that space itself has material characteristics. And that is the insight of general relativity. So in essence, he didn't kill off the ether. In essence, there still is an ether. And we need to understand actually what the physical properties of space are. So all of that just basically goes to I guess, try to encapsulate or justify my own point of view, which is that I think that, unfortunately, maybe the speed of light is in a universal speed limit, and it's because of the nature of the universe. Like, what is it? What is the universe? It's some sort of medium that we live inside of. And our job should actually be to understand that. It should be to understand the nature of space-time. So, yes, sorry to disappoint you, but that's my own opinion.
Okay, so are we going to wrap it up?
Yes, Paulo, the last thing that I want to say is to Professor Bush and Adam K, may your partnership continue, and you have us in Brazil and Portugal to collaborate, okay?
Okay, let me just present, before we stop, to share, I would like to share the book. Okay, let's go. Do you see it? Are you seeing? Okay. So this is the book. I'm sharing it because we have here the three editors, which is a surprising and very agreeable thing. Myself, John Bush, and of course Professor Kroc. And this is the second book this year about the subject. So our two books, I think, are the first ones about this messy thing in the century, I would say. So very good for us, and let's hope that the rest of the world gets in the subject, and let's hope that everything moves on. And what I would say is that we have to kind of deny some early postulates to move on. So I would like to thank everyone here. It was a really great pleasure, and I hope we see each other soon. So
yeah, thanks Paulo and Felipe for organizing, and I do hope to meet everyone live, even Paulo, who I've known for years. I haven't met live, so I've got a sabbatical coming up, not next year, but the year after. I expect to be knocking on your office doors.
Okay, that would be a very good pleasure also. Okay, right. So thank you.
You all.
Thank you, everyone.
Enjoy your weekend.
Bye-bye.
Thank you, everyone. Good Saturday.
Ok, pronto, foi uma coisa...
Muito bom, Paulo.
Foi bom.
Já parou a gravação, né, Rafa?
Não,
Já parei, acabei de parar.